So now let us discuss something practical, something that you can yourself do this exercise. Can be a laboratory exercise or it could be practicals that you can do at home. So you are supposed to take the power from the mains grid, which is 230 volts, have a switch and an MCB. There's a switch or an MCB. MCB can play the role of a switch, and have a transformer, a step down transformer. I want you to make a multi-output power supply, that is 3 outputs, 2 15 volts and 1 5 volts. And we'll try to see if we can implement what we have learned till now, and also try to use some IC regulators for the other 2 windings. So this is a transformer. You have to take a multi-output transformer having 3 outputs, and to one of the secondaries, let us connect this thermistor, the diode bridge, the full bridge, rectifier that we have studied till now. Connect a capacitor to the output of the diode bridge, and that becomes your unregulated. This becomes your unregulated DC voltage available to you. The transformer should be a 50 Hz transformer, laminated. You will get laboratory transformers. Let me show you. Let me show you a product. Let me show you a transformer. So here is a transformer. This is a laboratory transformer. So it looks like this. This is having EI laminations. These are the laminations, varnished. This is the coil which is wound, and the wires coming out to the terminal lug which is there on top. So you see that there are multiple windings brought out to these terminals. Input. So this is the input here, which says 0 to 230 volts. So that is these 2 terminals. This is red and black, which you can use as inputs, and these terminal lugs to be connected to the 230 volt grid. And the others are outputs. You have 3 outputs. So you have 1 2 3 here, 1 2 3 and 1 2 3. So here if you see, it is 12 0 12. So this is 12, this is a center point, 0 and 12. So it means from here to here it is 24 volts, here to here it is 12 volts, and here to here 12 volts. That's what it would mean. So 12 0 12 with the center tap also available if you want to use it for as a center tap transformer. Otherwise you can use only the extreme ones for 24 volts and extreme and the midpoint for 12 volts. Likewise, you have here 1 2 3. This is 15 volts, 15 0 15. So from here to here it is 30 volts, from here to here 15 volts. Likewise, if I come here, 1 2 3, these 3 terminals are going to give you an output which is 9 0 9. So here to here it is 18 volts, and here to the center point it is 9 volts RMS. So this is how a laboratory transformer would look like. You can buy a laboratory transformer like this and probably use it for making your power supply. Then coming back to the circuit board here, let me complete this circuit. We know this. So we use a series pass. I'm using a BJT here, and it is driven by this resistance and op amp combination, minus and plus. And we know how the reference to the plus terminal of the op amp is given. So we draw the reference circuit, a resistor, a Zener diode, and from the midpoint here you tap off and connect it to a potentiometer, and that can be, potentiometer point can be used as a reference here. In the meantime, let me also draw for the short circuiting. I am tapping off the drive signal from here, connecting it to another BJT, and I have a current sensor in the form of a resistor, and I will connect this here. So this forms your fold back current limiting circuit. Then you have the output voltage sensing by these two resistor divider network, and then that is given to the minus, and we take the Vref here, and the output is, this is the output, and this can be connected to whatever the load, and here I am connecting it to a resistive load or not. So that is V naught. So now let us mark the components, the various parameters. This is I naught flowing through R naught. This will be R1. This is R2. We know how to choose the values of R1 and R2 to get AV naught. And this is RS. This is the current sense resistor. RA, RB. We know how to choose the value of RA, RB when we discuss the design of the fold back circuit. R3, R4, we also have discussed how to choose or select the values of R3 and R4 for the reference while discussing the reference circuit. Is R5. So this resistor R5 is something that will limit the current such that the op amp doesn't get damaged. We have C, Q1, Q2. This 230 volts, 12, 0, 12. Let's say I take 12, 0, 12 and I'm not using the center tap, so which means that I have 24 volts here. So 24 root 2 is approximately 34 volts of unregulated voltage which will come in here. So let us say the output should be at 15 volts. So this will be the 15 volts regulated. And let's say 1 amp, which means 15 watts. So if you have a plus minus 20% tolerance, you will see that this voltage here will move from 27 volts to 40 volts. This is for an input mains 230 volts plus minus 20% tolerance. Now what is VCE? VCE will be 27 minus 15 on the low end, which will be 12 volts, and at the high end 40 volts minus 15, which is 35 volts. So the VCE across the Q1 can vary from 12 to 35 volts. So therefore one needs to think about the heatsink design for Q1. PD max will be 35 volts into 1 amp, which is 35 watts. At the lower end, it will be 12 volts into 1 amp, which is 12 watts. So 12 watts to 35 watts is the dissipation, but one must choose the heatsink such that 35 watts can be dissipated without blowing up the transistor Q1, without the junction temperature of transistor Q1 crossing the TJ max limit. So for a 15 watts output, you need here 50 watts, 35 watts plus 15 watts. You need 35 watt design for this diode bridge capacitor filter circuit, and we know how to design the full bridge and the capacitor filter circuit as we have discussed this here. So this resistor R5 is a resistor that limits the current drawn from the op-amp. See, the op-amps have a sourcing capability of 10 milliamps to 50 milliamps. So you should not draw more than 75% of its rating, let's say 35 milliamps from the op-amp. If it's a 50 milliamp op-amp, if it's a 20 milliamp op-amp, don't draw more than 15 milliamps from this. The worst case would be when you short the output. So when the output becomes shorted, this point is V0 plus I0 RS. So this would be V0 plus I0 RS plus 0.7, whatever the 0.6, the VBE of the BJT. And when you short the output, V0 becomes 0, so it will just be I0 RS plus 0.5. So under the worst case, whatever the supply voltage divided by R5 should be less than 75% of the rated sourcing capability of the op-amp. So like that you choose R5. This is very important. This is the protection for the op-amp. Okay. So the worst case condition is if V0 is equal to 0. Now how to give the supply for this, because there is a swing, unregulated voltage swing is from 27 volts to 40 volts, and we need to give a 15 volt supply to the op-amp. So you can tap off a resistor and a zener, and from the midpoint of that you can design the zener to handle around 25 to 30 milliamps and use that one as the VCC supply for the op-amp. So that would be one of the power supplies, 15 volt power supply. This is something, the discrete one, which we have studied. The second one also has all this. I have not put the thermistor, but it means that we include a thermistor for surge limiting protection. So capacitance, and you have a 3-pin IC regulator. So one of the regulators is LM317, which is having 3 pins, in, out, and an adjust pin, which is taken out, and I have a resistance division network like this, and you have an output R0. So the way this operates is that LM317 gives between the output and adjust pin 1.25 volts, fixed constant reference. And 1.25 volts divided by R1 will be the current flowing through that. This is a very high input impedance point, no current flows there. So the same current flows through R2 also. So V0 will be 1.25 divided by R1 into R1 plus R2 will be V0, which is 1 plus R2 by R1. This is the value of V0, and let's say this is set to 15 volts by adjusting the value of R1 and R2. There is another, this is a voltage regulator for a variable output. By adjusting R0, you can get variable output voltage. So LM317 approximately around 1 to 1.5 amps it can handle. There is another variable IC voltage regulator called LM723, which has a circuit, internal circuit almost like this. Only the current sense RS part is brought out. You can have one more boost Q1 connected as a Darlington. So like that. So let me just show you the data sheet so that it will give you an idea. So here you see the data sheet of LM723. So LM723 is very similar to the circuit that we, discrete circuit, linear power supply circuit that we discussed. You see there is a series pass, okay, and you look at this current limiter, series pass which goes to the output, right? There is also a Zener here, and you have a current limiter, current sense. Here you connect the resistance RS between the current limits, which can, so this internal BJT can divert the drive from this series pass. You have an error amplifier inbuilt, and you have a voltage reference, internal voltage reference Vref, which you can use for giving to the plus input. So this is something similar to almost all the parts of the circuit that we discussed falls into the IC. This is similar to the circuit that we discussed. All these parts will fall into the IC. Now let me show you LM317 also. So here is the data sheet of LM317. It's a 3-terminal adjustable regulator. So output voltage range adjustable from 1.25 volts, which is the voltage which is across output to adjust 1.25 volts. And by adjusting the R1 and R2 combination, you will be able to get a variable output voltage. And output current greater than 1.5 amps. So internal short circuit, current limiting, thermal overload protection, all those things are inbuilt within the IC. So it has very less number of components. So there is, let me see if any other interesting data sheet value. Look at this. Junction temperature is 150 degrees centigrade. You should not exceed junction temperature 150 degrees centigrade. So you have to be careful. See that these are the packages. You get it in TO220, TO263 package, to which heat sinks may need to be attached. Between the input and the output, the differential voltage should be greater than 3 volts. That is important. And this differential voltage into the load current that flows through will be the power dissipated through the device. And if the thermal resistance is not sufficient, you need to put external heat sink. So here is some thermal information. Theta junction to ambient, junction to case, so junction to board. These are all the thermal impedances available which you can use and try to. So you see 38 for TO263, 38 degrees centigrade per watt, 36 degrees centigrade per watt for junction to case. So use that like what we have discussed, and then calculate the heat sink. Another class of regulators, IC regulators, are the 7-8 series. The 7805. So if it is 7805, then means it's a 5 volt regulator. If it is 7815, then it's a 15 volt regulator. 7812, it's a 12 volt regulator. So this needs no external components at all. Output current up to 1.5 amps, 3 terminals, and input, output, and common. That's it. No other components are required. Very robust and very popular. So you see that for 5 volts 7805, for 8 volts 7808, for 10 volts 7810, like that. So this also you can see TJ max 150 degree centigrade, you should not exceed. Okay, and you also have the r theta jc and r theta ja value, r theta junction to case, r theta junction to ambient. These values, use these values to appropriately design the heat sink. So let us also have, so here you see that should be greater than 3 volts, the differential voltage, so that at least 18 volts you should have at the unregulated input. And we will have the third winding and the third full bridge regulator. Here I will use 7805, and just 7805 is sufficient, and minimum number of components V0 is 5 volts. You need to maintain at least greater than 3 volts input output differential, means that this capacitor point voltage should be greater than 8 volts under any condition. So choose the values of the winding accordingly. So heatsink design is important for 78 LM317 and 7805, and also for Q1. And let me say that, okay, this is called a variable IC based regulator. This is called a fixed IC regulator, fixed voltage IC regulator. So what experiment do you want to do? So V0, for each of these cases, V0 is one parameter you need to worry about. One is, the other one is V in, this voltage here, Vi, and I0. So line regulation is with respect to Vi. So let us tabulate Vi and V0 and conduct some 5 variations. So you need to vary Vi. So how will you vary Vi? This is the voltage at this point. So you can have an auto transformer. You can have an auto transformer here and vary the auto transformer so that the input voltage can be varied. And you tabulate V0 and Vi. Now load regulation. This is another important activity that you need to do with respect to regulators. I0 is the independent variable. You vary I0 and see what is the effect on V0. So conduct few for different loads and change R0 to vary I0. Then you plot Vi versus V0. X-axis keep Vi and V0 is on the y-axis, and plot I0 versus V0. Again, x-axis the independent variable I0 and V0 on the y-axis. These two plots will give you an idea of regulation as Vi varies and as load I0 varies.